Hi, this is Professor Pradyod from Leadib Academy. Okay, so we are going to discuss today IBDP Chemistry SL Paper 2 of November 2019. And I'm providing here the reference number, okay, for this paper, okay. And we'll be discussing basically the solutions. So I'm going to provide you the video solutions. But interestingly, these are not just going to be the solutions for those questions, but we'll be discussing the underlying concepts. Okay. So this will help you in revising some of the concepts which you probably might have forgotten or not understood. So it will be some kind of a revision, very, very interesting. Okay. And it should really help you in getting your concepts right, improving the grades. And we, interestingly, Leadib Academy, we are providing you the courses for deeper understanding. So we are providing you for the majority of the subjects of IBDP, like chemistry, physics, maths. So please do visit our website, okay, www.leadibacademy.com. Okay. So let's begin with our question number 1. Okay, so the question number 1A. The equation shows steps in the formation and decomposition of ozone in the stratosphere, some of which absorb the ultraviolet light. Okay, so they have given us step 1, step 2, step 3, step 4 reaction. Draw the Lewis structure of oxygen and ozone, O3. Very, very simple. Let's begin of drawing the Lewis structure. So what we do in case of Lewis structure, okay, very simple, oxygen and oxygen. First count the total valence electrons. So let's calculate total valence electrons in 2 oxygen atoms. So that is 2 multiplied by 6 because oxygen contains 6 valence electrons. Valence electrons mean the electrons which are in the outermost atom. Okay, sorry, outermost orbit or shell, that is 12. Okay, now what we should do? Okay, so what we will do, first we will put, okay, electrons, and we will form a single bond between these 2 atoms. Okay, these 2 oxygen atoms. Okay, that is the first story. So we have consumed out of 12 basically 2 electrons. Okay, simple. Now let's see how many total are left now. How many electrons are left? So we can say clearly how many electrons are left. So we can clearly see that out of 6, so let's put 2 and 2. That makes us 4, and here 6. Okay, so now check up. So what was the second step? We are putting the balance 10 electrons, so 12 minus 2, 10. Okay, 10 electrons are left. So check up now how many electrons are left. Okay, so it is very simple that we can put now 1 electron each from each atom, and we will get like this. Okay, so that is getting converted into oxygen. Each oxygen is having 2 lone pairs. Oh, sorry. This is the structure of oxygen. So in short, it is like double bond with lone pairs, two lone pairs on each oxygen atom. Very, very simple. Okay. So this takes care of oxygen. Now let's move on to the ozone. So what we should do in case of ozone, that is the O3, oxygen, oxygen, oxygen. How many total electrons? So total valence electrons, this is for ozone. Total valence electrons are 3 multiplied by 6, that is 18. So now let's start putting the electrons. So first form the single bond. So let's put it like this: 1, 1, and 1. Okay, so we have consumed, basically out of this 4 electrons have been consumed, so that is 14. So now let's start distributing in terms of the lone pairs, these 14 electrons. So 1, 2, so basically we need to distribute these 7 lone pairs. So let's start put it: 3. So now we have consumed, basically out of 7 lone pairs, 14 electron means 7 lone pairs, out of which we have consumed 6. So let's now start putting only 1 lone pair. Okay, so this is what is the structure. Now check up whether each oxygen has completing the octet. So you can clearly see that this number 1 and number 2 oxygen, they are completing octet, but the poor number 3 is having a shortfall. It is having only 6 electrons. So what we can do, okay, we can put 1 lone pair, okay, into this to form the bond, double bonds. So let's see, so what structure we will get: oxygen, oxygen, oxygen. So now we will get a structure like this. Okay, and now just see whether it, sorry, let me just rewrite, and now find out whether each, okay, let me again, what, okay, just put, let me put a dot. Now you can see easily that each atom is containing 8 electrons, including the central one. Okay, and all 3 are completing their octet, and it means that the structure, final or Lewis dot structure, would be like this. Okay, it can be represented like this: that 1 oxygen is having 2 lone pairs, central one is having 1 lone pair, and the other oxygen is having 3 lone pairs. Simple. Okay, this is the final Lewis dot structure. Okay, hope this is quite clear. simple one. Okay, let's look into the question B. Outline why both the bonds in the ozone molecules are of the same length. Predict the bond length in the ozone molecule. Refer to the section 10. So let's first, okay, the first thing is to draw the Lewis structure for the ozone, which we have already done. Okay. Okay, I'm just reproducing it again. So on one of the oxygens, there are 3 lone pairs. Okay, so 1, 2, and 3. Okay, 3 oxygens. And in this structure, the double bond is between 1 and 2, which you can clearly see. Let me, I think, make it a little bit bigger so that you should not feel that why this is smaller. Okay, and let me show this. Okay, 1, 2, and 3. So in this structure, the double bond is between 1 and 2 oxygen, while single bond of 2 and 3. So what is going to happen in this case? Okay, there is something what we have already learned because of the resonance, okay, or delocalization of the electrons. So what is going to happen? That one of the lone pairs will get shifted here, okay, and one of the pi bond will get shifted on this oxygen. Okay, and what structure we will get is the resultant structure would be like this. Double bond. This continues to be one single pair, and now oxygen number 3, 1, 2, and 3. Now the double bond is between oxygen number 2 and 3, while single bond is there between oxygen number 1 and 2. Okay, and similarly the lone pairs have changed. So the question is, these are what we call resonance structures. Resonance means just shifting of the lone pairs or pi electrons which are there in the pi bond. Okay, so the question is that actually which is the correct structure out of these two? And the answer is none of them. It is actually in between these two. Okay, it is neither the first one or the second structure. So the correct structure would be like this. Okay, so we can say that the, okay, and let me give the numbering for the oxygen atoms. So this is 1, 2, and 3. And now we can say that there is no double bond between 1 and 2. It is in between, like dotted one. Similarly, there is no strictly the double bond. It is between single bond and double bond. Okay, so we can say it is neither single nor double bond. So in it simply means that a bond has to be in between the single bond and a double bond. Okay, it should be very, very clear. The bond length has to be between single bond and a double bond. Now we can very well refer to the data booklet. So let me try to show it here if possible. Sorry. Let me try and show the structure. Okay. Okay. So that we can predict the length, bond length. So this is the section 10 of the data booklet. So what is the bond length of oxygen and oxygen single? So we can clearly see that the bond length is 148, that is between oxygen and oxygen single bond. And what about the double bond? It is 121 picometer. So in short, the actual bond length would be between 188 picometers and 121 picometers. How much, that we don't know, but it will be in between these two numbers. It is sandwiched between 148 and 121 picometers, straightforward. Okay, it is neither single bond nor double bond. Hope this is quite clear. Okay, let's look into the question number C. Distinguish ultraviolet light from the visible light. Very straightforward. Okay, UV, ultraviolet, and visible. So let's understand first frequency. It is high. This is low. We are comparing. So therefore, wavelength is low, exactly reverse, and this is high. And in terms of the energy, we should be aware of that energy depends on the frequency. So higher the frequency, higher the energy. So that means high energy, low energy. That's all. Okay, very simple. And because of this higher energy, ultraviolet radiations are, okay, they are more harmful. This is the reason, because they are having high energy, and that's why they are very harmful. Okay, so ultraviolet, ultra means above the violet. Okay, because we know that in case of our visible one, it is a VIBGYOR. So whatever is on the left hand side, that means higher frequency is UV, and below red, that is the infrared. Okay, that's the reason. Very simple. Okay, continuation with the question number 1D. Discuss how the different bond strengths between the oxygen atoms, O2 and ozone in the ozone layer affect radiation reaching the Earth's surface. So first, very important concept that we have already discussed, but just to recap, in case of oxygen, there is a double bond between oxygen atoms, while in case of ozone, okay, it is neither double bond nor single bond. So we can say for all practical purposes, it is one and a half bond. Okay. So obviously, which bond is going to be weaker? So this is the weaker bond in case of ozone. Okay, this is the oxygen, O2. So it is a very clear cut. This is being a weaker bond. So what is going to happen now? Understand, just to recap. Okay, sorry. Okay, so this is what it is. So what is happening in case of ultraviolet? Okay, there are three kinds. One is the UVC, which is the highest energy. This is a slightly lower, so this is the medium one, and this is the lowest. energy. So what happens that you can clearly see that oxygen takes care of UVC, it absorbs because this is having a higher or stronger bond, so it needs strong higher energy, okay, to get decomposed. Okay, simple. So that means it absorbs this. Oxygen absorbs the highest higher energy radiations of ultraviolet UVC. Then in case of the ozone, we know that it is like a 1.5 bond or slightly a weaker bond. So it takes care of the medium kind of a energy, okay, medium strength of the ultraviolet radiation called UVP. So oxygen takes care of UVC, which is a higher energy. Then ozone takes care of UVB, okay. And finally, what reaches Earth is only UVA, okay, which are the lowest possible energy. And finally, they reach Earth, okay. This is how it works. So this should be very, very clear, very simple, based on the bond strength. Stronger the bond, you require higher energy, so it is going to absorb the highest possible energy, that is UVC. Weaker bond in ozone, 1.5 bond, so it is going to absorb slightly lower, that is UVB. And the lowest energy is in case of UVA, which reach Earth's surface. Very simple.